All right, so let's talk about Kirchhoff's laws. Kirchhoff. Jeez, I'm starting terrible. Kirchhoff's laws. It's because I always forget that second H. Kirchhoff's laws. One of them we've already talked about. That's his junction law. And this had to do with the current going into a junction. And it just said that the total current going into a junction is equal to the total current going out. So if I had a junction and I had a current coming in and then it split into two currents, we'll call it I2 and I3, then I know that the current going in, I1, is equal to the sum of the currents going out, I2 plus I3. Pretty simple. And this is just based on the conservation of charge. Conservation of charge. Charge, that's an R. Okay, so the charge that comes in gets split into two, so it all has to add up. This plus that has to be equal to this because the charge is conserved. And now we'll get into the loop law. And the loop law says that the total potential difference around a loop, which is the sum of all of the potential differences, is equal to 0. And this comes from the conservation of energy. Of energy. So as we move around, the potential difference, which is measures the energy, the potential energy, as it goes around the entire loop, we have to have a net zero. Yeah, I mean that's a conservation of energy. So let me show you an example, and it might make a little bit of sense. So suppose we had a battery connected to a couple of resistors. And it comes back to the battery. All right, let's get some, let's call this R1, we'll call this R2. This is gonna be a battery, so we'll put an EMF on it. And then let's get some points. So let's say A. Actually, let's put A over here. So we'll do A, we'll call that B. And then C, D, and E. And what I want to do is I want to look at the potential difference as we go around the circuit. So R would be how far I am along the circuit, and I want to look at the potential difference starting at A. So at A, the potential difference right before you come into the battery is 0. So we're going to have 0 potential difference, and that would be at point A. And then it crosses the battery. So as it crosses the battery, remember I goes this direction, the current. So as we go across the battery, we're going to have an increase in the potential energy across the battery. And then so we exit it and we're at point B. Then we come along to C, and we assume this is an ideal wire, so there's been no change in the potential. So we get to point C, and you did this in the mini lab or the virtual lab. So you get to point C, there's no change, and then we go across a resistor. And so our voltage, we have a voltage, we call it a voltage drop. That means that the voltage has gone down, but it hasn't gone to 0 yet because we have another resistor over there. So at D, we've lost some potential energy. And then it goes across resistor 2, and that brings us all the way down to 0 so that we can enter back in. So this would be point E. So if I'm thinking about the sum of the potential differences as I go around, I'd have this first increase. So I'd have a positive amount, which would just be the potential difference across the battery, which is my EMF. And then we move along, and then I have a potential difference drop. So that would be minus the potential difference of the resistor 1. And then I subtract the potential difference of resistor 2. And then I'm back at 0. And this is the law. Now, a couple of notes about using this. So when we start analyzing it, When you use this, what you want to do is, number one, you want to label the current flow. Label the direction. Because this matters, especially when you start crossing multiple batteries. Because after you label it, you're going to go around and you're going to label everything else. Label the elements. And so the potential difference of a battery, put a big B, is equal to positive electromotive if we're going from negative to positive. So in conventional, if I go from the negative terminal to the positive, I'll have positive E. However, it equals negative EMF if you're going from the positive to the negative. So if you're going backwards across the battery, then it's the negative electromotive force. And then the potential difference across a resistor is just IR. And that just comes from our definition of current. And then the third step in this analysis is to apply the loop law, which is that the sum of the potential differences, that's a V delta, is equal to 0. So we can do that, and you can see we can solve for the current or the resistance. We can do all kinds of things. So I'll do an example, but this is basically what you're going to do. This right here is going to be the key when you're dealing with multiple batteries, getting that right. Oh, I'm sorry. You know what? The resistance across the battery is negative IR because we have to subtract. It's always a voltage drop. Let me write that. So we'll always have a voltage drop across resistors. All right, so let's do an example. Just get a new page open. I need to figure out how to make this bigger, so I don't have to open it up all the time. All right, let's look at a circuit with two batteries. So we have a battery here connected to a resistor. Connected to another battery, connected to a resistor, and then back to the battery. All right, so let's label everything. This is long, so that's positive. This is negative. We'll call this R1, call this R2, call this D2. Just kidding. That's positive, that's negative. All right, let's put some units on, or some values. So this is going to be 40 ohm, and then we'll have a 9 volt, a resistance of 20 ohm, and then a 6 volt battery. All right. So then what we want to know is what's the current in the circuit, and what's the potential difference across each of the resistors. So to do that, we're going to use Kirchhoff's loop rule. And it doesn't matter which way you go. You can go this direction or you can go this direction, but you got to get a starting and ending. So I'm just going to start on this battery, and I'm going to flow it this way. So my flow is going to be like that. So that's my current. All right. So as I go around my current, the first thing I want to do is I want to label stuff. So if I come across this battery, I'm going negative to positive. So this is going to be positive electromotive. That's going to be my delta V across the battery. And then we come up here and we cross this resistor. Resistor is always negative I, and this would be R1. And then we come along and we pass through another battery, but this time we're going from positive to negative. So my delta V of the battery 2 is going to be negative electromotive force. And then I come along here and I cross another resistor. So again, I have negative IR2, and we're done. So this is a potential difference, battery 1. So positive EMF, negative IR, negative EMF, and then negative IR2. So now we can apply Kirchhoff's. So it says that the sum of the potential differences is equal to 0. So we start here. So we have positive E from 1 minus IR1 minus the electromotive on 2 minus IR2. All of that's equal to 0. And so I can see here I can solve for the current. And then once I have the current, getting the potential difference would just be multiplying it times the resistance. That's for both of these, delta V. Oops. All right, so let's solve for I. So what I can do is we can, let's move these IRs to the other side. So I get the electromotive of 1 minus the, sorry, I keep doing that. The EMF of 2 is equal to IR1 plus IR2. I can factor out the I, and so I'll factor out the I and then divide by the inside. So it'd be R1 plus R2 over here. So I get the EMF1 minus EMF2 divided by R1 plus R2 is equal to the current. So this minus that, so I'd get negative 3 divided by the sum of the resistances. So I'd add those up, 60. And I know that it says negative, but it's just because of my direction. So we'll deal with the negatives when we get to it. So you end up getting 3 divided by, that would be 3 volts, divided by 60 ohms. It's going to be the current. That was negative, but again, that's just because of the direction that I chose. If I went the other way, it would have been 9 minus, so we just dropped that. Current is positive. So we get a current of 0.050 amps. Now I can just take that and multiply by the resistance to get the potential difference across the resistors. And that's it. I mean, it's just being careful, especially when you're crossing batteries. Just pay attention to the direction that you're going across the batteries. If you end up with a negative current, we just make it positive because that just depends on the direction that we chose. And that'll be it.